Hi everyone, I'm Zohreh and I hope you're doing great. In last video, I spoke about a second chapter of Holliday Physics book, which is about a motion along a straight line. I talk about subjects such as position and displacement, average velocity and average speed, instantaneous velocity and speed, acceleration, constant acceleration, free fall acceleration, and graphical integration in motion analysis. In this video, I'm gonna teach you the third chapter of Holliday Physics book, which is about vectors, and I will talk about subjects, vectors and scalars, adding vectors geometrically, components of vectors, unit vectors, adding vectors by components, vectors and the law of physics, multiplying vector, multiplying a vector by a scalar, multiplying a vector by a vector, the scalar product, the vector product, and right-hand rule. If you are interested in physics, then you can join and enjoy.
Welcome to our Physics Holiday Book adventure. Today we'll explore the fascinating world of vectors. Physics deals with a great many quantities that have both size and direction, and it needs a special mathematical language which is called the language of vectors to describe those quantities. In this chapter, we focus on the basic language of vectors. Vectors and scalars. A particle moving along a straight line can move in only two directions. We can take its motion to be positive in one of these directions and negative in the other. For a particle moving in three dimensions, however, a plus sign or minus sign is no longer enough to indicate a direction. Instead, we must use a vector. A vector has magnitude as well as direction, and vectors follow certain rules of combination. Some physical quantities that are vector quantities are displacement, velocity, and acceleration. You will see many more throughout physics subjects, so learning the rules of vector combination now will help you greatly in later. Not all physical quantities involve a direction. For example, temperature, pressure, energy, mass, and time. We call such quantities scalars, and we deal with them by the rules of ordinary algebra. The simplest vector quantity is displacement, or change of position. A vector that represents a displacement is called reasonably a displacement vector. If a particle changes its position by moving from A to B, such as figure part A, we say that it undergoes a displacement from A to B, which we represent with an arrow pointing from A to B. The arrow specifies the vector graphically. In figure part A, the arrows from A to B, from A prime to B prime, and from A double prime to B double prime have the same magnitude and direction. Thus, they specifically identical displacement vectors and represent the same change of position for the particle. A vector can be shifted without changing its value if its length and direction are not changed. The displacement vector tells us nothing about the actual path that the particle takes. In figure part B, for example, all three paths connecting points A and B correspond to the same displacement vector. That of figure part A, displacement vectors represent only the overall effect of the motion, not the motion itself. Vectors geometrically. Suppose that, as in the vector diagram of figure part a particle moves from A to B and then later from B to C. We can represent its overall displacement, no matter what its actual path, with two successive displacement vectors AB and BC. The net displacement of these two displacements is a single displacement from A to C. We call AC the vector sum or resultant of the vectors AB and BC. This sum is not the usual algebraic sum. In figure part B, we redraw the vectors of figure part A and relabel them with an arrow over an italic symbol. If we want to indicate only the magnitude of the vector, a quantity that lacks a sign or direction, we shall use the italic symbol as in A, B, and S. A symbol with an overhead arrow always implies both properties of a vector, magnitude and direction. We can represent the relation among the three vectors in figure B with the vector equation S is equal A plus B, which says that the vector S is the vector sum of vectors A and B. The symbol plus in equation and the word sum and add have different meaning for vectors than they do in the usual algebra because they involve both magnitude and direction. Figure suggests a procedure for adding two-dimensional vectors A and B geometrically. The tail of vector B is at the head of vector A. Then the vector sum is the vector that extends from the tail of A to the head of B. The properties is that vector addition defined in this way has two important properties. First, the order of addition does not matter. Adding A to B gives the same result as adding B to A according to figure that is commutative. Second, when there are more than two vectors, we can group them in any order as we add them. Thus, if we want to add vectors A, B, and C, we can add A and B first and then add their vector sum to C. We can also add B and C first and then add the sum to A. We get the same result either way, as shown in figure that is associated law. The vector minus B is a vector with the same magnitude as B but the opposite direction. As you can see figure, adding the two vectors in figure would yield 0. Thus, adding minus b has the effect of subtracting b. We use this property to define the difference between two vectors. Let d is equal a minus b. Then the vector subtraction will be D is equal A minus B, or it's equal A plus minus B. Figure shows how this is done geometrically. Remember that although we have used displacement vectors here, the rules for addition and subtraction hold for vectors of all kinds, whether they represent velocities, acceleration, or any other vector quantity. However, we can add only vectors of the same kind. For example, we can add two displacement or two velocities, but adding a displacement and a velocity makes no sense. Components of vectors. Adding vectors geometrically can be tedious. A neater and easier technique involves algebra but requires that the vectors be placed on a rectangular coordinate system. A component of a vector is the projection of the vector on an axis. In figure part A, for example, AX is the component of vector A on or along the x-axis, and AY is the component along the y-axis. To find the projection of a vector along an axis, we draw perpendicular lines from the two ends of the vector to the axis, as shown. The projection of a vector on an x-axis is its x-component, and similarly, the projection on the y-axis is the y-component. The process of finding the components of a vector is called resolving the vector. As figure part A and B show, if you shift a vector without changing its direction, its components do not change. For finding the components, we can find the components of A in figure part A geometrically. From the right triangle, AX is equal A cosine theta and AY is equal A sine theta, where theta is the angle that the vector A makes with the positive direction of the x-axis, and A is magnitude of vector A. Part C shows that A and its x and y components from a right triangle. It also shows how we can reconstruct a vector from its components. We arrange those components head to tail. Then we complete a right triangle with the vector of forming hypotenuse from the tail of one component to the head of the other component. If we know a vector in component notation AX and AY and want it in magnitude angle notation A and theta, we can use the equation A is equal square root of AX squared plus AY squared, and tangent of theta will be equal AY over AX. Unit vectors. A unit vector is a vector that has a magnitude of exactly 1 and points in a particular direction. It lacks both dimension and unit. The unit vectors in the positive direction of the x, y, and z axes are labeled as I hat, j hat, and k hat, where the hat is used instead of an overhead arrow as for other vectors. The arrangement of axes in figure is said to be a right-handed coordinate system. Unit vectors are very useful for expressing other vectors. For example, we can express vector A and B as A is equal AX I hat plus A by J hat. or B is equal bx I hat plus by j hat. These two equations are illustrated in a figure, and the quantities ax I hat and a by j hat are vectors called the vector components of vector A. The quantities ax and ay are scalars called the scalar components of vector A, or simply it's called components. Vectors by components. We can combine their component axis by axis. To start, consider the statement R is equal A plus B, which says that the vector R is the same as the vector A plus B. Thus, each component of R must be the same as the corresponding component of A plus B. Rx is equal Ax plus Bx, Ry is equal Ay plus By, and Rz is equal Az plus Bz. In other words, two vectors must be equal if their corresponding components are equal. These equations tell us that to add vectors A and B, we must first resolve the vectors into their scalar components. Second, combine these scalar components axis by axis to get the components of the sum R. And third, combine the components of vector R to get a vector R itself. We have a choice in step 3. We can express vector R in unit vector notation or in magnitude angle notation. This procedure for adding vectors by components also applies to vector subtraction. Recall that a subtraction such as d is equal a minus b can be rewritten as an addition. D is equal a plus minus b. To subtract, we add a and minus b by components to get dx is equal ax minus bx, dy is equal ay minus by, and dz is equal az minus bz, where d is equal dx I hat plus d by j hat plus dz co hat. Vectors and the laws of physics. So far, in every figure that includes a coordinate system, the x and y axes are parallel to the edges of the book page. Thus, when a vector A is included, its components ax and ay are also parallel to the edges. As you can see in figure A, the only reason for that orientation of the axis is that it looks proper. There is no deeper reason. We could instead rotate the axis but not the vector A through an angle phi as in figure B, in which case the components would have new values. Call them A prime x and A prime y. Since there are an infinite number of choices of phi, there are an infinite number of different pairs of components for vector A. The question is that which then is the right pair of components? The answer is that they are all equally valid because each pair with its axis just gives us a different way of describing the same vector. All produce the same magnitude and direction for the vector. As you can see in figure B, A is equal square root of ax squared plus ay squared is equal ax prime squared plus ay prime squared, and theta is equal theta prime plus phi. The point is that we have great freedom in choosing a coordinate system because the relations among vectors do not depend on the location of the origin. or on the orientation of the axis. This is also true of the relations of physics. They are all independent of the choice of coordinate system. Multiplying vectors. There are three ways in which vectors can be multiplied, but none is exactly like the usual algebraic multiplication. Multiply a vector by a scalar. If we multiply a vector A by a scalar S, we get a new vector. Its magnitude is the product of the magnitude of vector A and the absolute value of S. Its direction is the direction of vector A if S is positive, but the opposite direction if S is negative. Also, to divide vector A by S, we multiply by 1 over S. Multiplying a vector by a vector. There are two ways to multiply a vector by a vector. One way produce a scalar, which is called the scalar product, and the other produces a new vector called the vector product. The scalar product. The scalar product of the vectors A and B is written as A dot B and defined to be A dot B is equal AB cosine phi, where A is the magnitude of vector A, B is the magnitude of vector B, and phi is the angle between vector A and B, or more properly, between the direction of vector A and B. Note that there are only scalars on the right side of the equation. Thus, A dot B on the left side represents a scalar quantity. Because of the notation, A dot B is also known as the dot product and is spoken as A dot B. Interpretation of dot product is that in figure B, vector A has a scalar component, A cosine phi, along the direction of vector B. Note that a perpendicular dropped from the head of vector A onto vector B determines that component. Similarly, vector B has a scalar component, uh, B cosine phi along the direction of vector A. If the angle phi between two vectors is 0, the component of one vector along the other is maximum. And so also is the dot product of the vectors. If instead phi is equal 90, the component of one vector along the other is 0, and so is the dot product. Equation can be written as follows to emphasize the components. A dot B is equal A B cosine phi. The commutative law applies to a scalar product, so we can write A dot B is equal B dot A. When two vectors are in unit vector notation, we write their dot product as A dot B is equal AXI hat plus AYJ hat plus AZK hat. A dot BXI hat plus BYJ hat plus BZK hat, which we can expand according to the distributive law. Each vector component of the first vector is to be dot with each vector component of the second vector. By doing so, we can show that A dot B is equal AXBX plus AYBY plus AZBZ. Vector product. The vector product of A and B, written A cross B, produces a third vector whose magnitude is equal AB sine phi. Because of the notation, A cross B is also known as the cross product, and in speech, it is A cross B. If vector A and vector B are parallel or anti-parallel, A cross B is equal 0. The magnitude of A cross B, which can be written as absolute value of A cross B, is maximum when vector A and B are perpendicular to each other. The direction of C is perpendicular to the plane that contains A and B. Figure shows how to determine the direction of C is equal A cross B with what is known as a right-hand rule. Place the vectors A and B tail to tail without altering their orientations, and imagine a line that is perpendicular to their plane where they meet. Pretend to place your right hand around that line in such a way that your fingers would sweep A into B through the smaller angle between them. Your outstretched thumb points in the direction of vector C. The order of the vector multiplication is important. In figure B, we are determining the direction of C prime is equal B cross A. So the fingers are placed to sweep B into A through the smaller angle. The thumb ends up in the opposite direction from previously, and it must be that C prime is equal minus C and B cross A is equal minus A cross B. In other words, the commutative law does not apply to a vector product. In unit vector notation, we write A cross B is equal AX I hat plus A by J hat plus AZ K hat dot BX I hat plus B by J hat plus BZ K hat, which can be expanded according to the distributive law, that is, each component of the first vector is to be crossed with each component of the second vector. For example, in the expansion of equation A cross B, we have AX I hat cross BX I hat, which is equal AX BX I hat cross I hat, which is equal 0, because the two unit vectors are parallel and thus have a 0 cross product. Similarly, we have AX I hat cross BY J hat, which is equal AX BY I hat cross J hat, which is equal AX BY K hat, because the cross product of I and J is equal K. These vectors I hat and J hat each have a magnitude of unity, and the angle between them is 90. Also, we use the right-hand rule to get the direction of I cross J hat as being in the positive direction of the z-axis, thus in the direction of K hat. The determinant can also be used. A cross B is equal minus B cross A. We arrange a determinant and we put I hat, J hat, K hat in the first line, A vector component, which is AX, AY, and AZ in the second line, and B component, BX, BY, BZ in third line. And then for the first step, we considered I hat component, and then we considered only this determinant. We erase the column and row that contains I hat, and the remain is a determinant with 4 components, A by AZ, B by BZ. For the second one, we again remove the row and the column contains J, but here don't forget to put a minus for J component. And the remain will be a determinant AX, AZ, bx, bz. And for the third one, again, we remove the row and column contain k, and the remaining determinant will be ax, ay, bx, by. With calculating these three determinants, we can solve the equation A cross B. And it is really simple and useful. And that concludes our journey through the worlds of vectors. Remember, understanding and mastering this subject is essential for any aspiring physicist. Stay curious and keep exploring.